So we're early on in this calculus course that is sometimes called vector calculus and sometimes called multivariable calculus. We haven't seen any calculus yet, and it turns out we're not going to see any calculus in the first unit because what they're doing in the textbook and what I'm doing is building up a new set of tools to measure 2 dimensions in, but also to measure in 3 dimensions. So as we begin the third section of the course, I want to just highlight a couple of key vocabulary that we've seen. Of course, the vector is screamed out as a big one. And then I've been using the term scalar, and I'd like to bring that a little bit more to light in this little segment. So a vector has or gives us 2 pieces of information. Do you remember what those are? Well, that's right. A direction and what's called magnitude. Magnitude could be interpreted as a length or a strength, a speed, a force, but the direction and the magnitude are the 2 aspects of a vector, and we've been using vectors in 2 and 3 dimensions. In linear algebra, you'll use many higher dimensions, and you'll work on alternate notations and tools for manipulating those. So a scalar is just simply, I'm going to put it in quotes, a number. Well, it's not always just a number. I'm just going to write here, mostly just a number. A better way of looking at scalar is it's just a single item, where a vector gives us 2 or 3 components in this course that always generate those 2 details. What we have seen is something that is called scalar multiplication, where if I have a vector that's called u, then I can go 2 times u and change the scale of it. Same direction, but twice as long. So that's where its nickname scalar came. So this looked a lot like the distributive property, and it gave us a vector. Well, in section 11.3, we add in another tool. That tool is called the dot product. Remember, you do have a pause button if you're trying to write this down. Use the pause button sometimes. So the word product is another type of multiplication, but it's a different multiplication than that one. This one takes a vector and we'll call it changes the magnitude, but not the direction. So the dot product is an extremely simple calculation, but when you're done with it, it won't be very satisfying. It'll be something that you'll wish, well, maybe he'll put 10 of those on the exam. That's easy. But in terms of why would you care about it, it doesn't jump out and it's not obvious at the beginning. So if you want to see what a dot product looks like, let's just go here, u, and there's the dot product v. You need this symbol here so that it is a dot product, because there's a third type of multiplication that we're going to meet. So this is scalar. This is a dot product, and you'll meet another one in the next section of the book. So the dot product is as simple as multiplying the corresponding x values together, u1 and v1, plus the corresponding y components, u2 and v2, and that's it. Nothing else. This is your solution. Again, easy, but what does it mean? Not very clear. So let's just generate an example. So our example, first one that we're going to do, let's let the vector u be just the simple 3, 4, and the vector v equal to negative 2, 1. When we calculate the dot product, 3 multiplied by negative 2 plus 4 multiplied by 1, negative 6 and 4 is, that's right, negative 2. Now, there are a lot of things to be said about this, but let me just start with this one. When we use scalar multiplication, we have a vector still when we're done. A number times a vector makes a different length vector. We don't have a vector anymore here. This is a scalar. It's not a vector. It's not a vector. Let's do one more calculation example. There we go. Have enough room? I think we do. Example 2. So let vector u be 5i plus 2k, and vector v be equal to 4i minus 3j plus k. Remember, this notation here is what your physics teacher are most likely to be using, at least at our college. It's a very commonly used notation. Some textbooks only use the IJK notation. Our textbook happens to use component form and this form as well. Please note, there are 3 components. But in this notation, you don't see my j here. When we do the dot product calculation, we have 5 multiplied by 4. There's no j component here, and just so you know, 0 is a real number. Check your wallet. 0 is a real number. 0 times negative 3 plus 2 multiplied by, what's the coefficient here? That's right, it's a 1. 20 plus 0 plus 2 is 22. Again, not a very difficult calculation, but there is really no meaning here to it so far. Now, before I close out, I'd like to just show you a couple little pieces of where we're going to find this calculation called the dot product. All right. I'm just going to straighten things out here. Sorry I left you for a moment. Dot product. I want you to think of dot product as not a calculation that is valuable by itself, but I want you to think of it as like a power source or a battery. It's used in other formulas for our purposes. The dot product is very meaningful in lots of ways, but for a simple getting started example, you're going to see the dot product show up in a couple ways. So let's suppose that we had 2 vectors, vector u and vector v, and let's suppose that they were starting from the same point. One of the formulas for dot product actually helps us find the angle between those vectors. And if in physics you're dealing with measurements of forces, you're going to need to know that angle. So there's something called the cosine of theta formula. You're going to see this derived in another video, and I'll do a couple of examples as well. Cosine of theta involves the dot product over the magnitude of the two vectors. This will be proven. We'll actually take it for a test drive on a couple of examples. There's more key vocabulary there. I just wanted you to meet it. The dot product is built in a formula. And then later, we'll see that it's part of something called a projection. A projection. I'm not going to write that formula out here because I'll dedicate some other video time for us there. But the dot product plays a key role in this formula as well. So multiplying those components together has some indication of how two vectors interact in between each other. So I'm going to leave it with that for the moment. There's definitely more segments coming up, so stay tuned.